graph I just sketched based on points where I threw chalk at the board is a graph that you're going to have a lot of difficulty coming up with a formula for. And most of the functions that we study in this course are going to have formulas, but then sometimes we'll do exercises with just random functions. We build functions from a set of toolkit functions. Almost all the functions that we study in the course are built up from more than a handful, but really not more than about 2 handfuls of toolkit functions. The 3 most basic toolkit functions have graphs that look like the ones I'm about to sketch. Now, each of these is supposed to be a square, 4 units by 4 units. The red dot in this square and the red dot in this square are right in the center, right halfway across the lower edge, the center of the lower edge of the square. This one is in the center of the square. First graph I'm going to draw is called a parabola, and it's got a kind of a well-defined shape. I'm just going to kind of soften it down here. I'm usually pretty bad at it. It's not great, but it's better than usual. Okay, that's what a parabola looks like. You might be familiar with it, probably are. Okay, now here's one that you might not be familiar with. Looks something like this. There's more continuity about it. And I'm going to tell you, it's fairly easy to do a good job of constructing these. And they're actually formulas, and you can construct the graphs using formulas with a little bit of arithmetic. But right now, we're just going to look at the shapes. Okay, now I got to block the board here for a second. I don't want to mess this up and it's necessary. Okay, there are 3 toolkit functions. This is a parabola. It's your basic quadratic function, or your basic squaring function. Formula is y equals x squared. Okay, I'm not going to give you the formulas for all of these right now. We're not going to use the formulas until we do these things geometrically. Okay, this is your exponential. And in this course, we are going to learn what it means for something to grow exponentially. People misuse this all the time. But there's a very specific criterion for something that grows exponentially. You'll see that fairly early. It's not difficult to understand. And this is reciprocal. Or inverse proportionality. Okay, those are the graphs. And a whole bunch of the functions that we study in the course are built from these 3 graphs, or a couple of others that are very similar to these 3 graphs. The reason I choose these 3 graphs is they can be constructed with simple geometry, just simple sketching, and we don't use calculators to graph these. We do this by hand, and we don't do the arithmetic calculator. We do the arithmetic using the rules of arithmetic. The arithmetic is very simple for these, and it's very feasible to do the arithmetic. Okay, so there are the functions. Now, when we put these functions in their standard position, this red dot on each will be the origin of the coordinate system. So my y-axis now would have to go through the red dot and see my x-axis. Same thing over here. the y-axis. And incidentally, if I did this accurately, this should be 1/4 of this. Let's see, now I didn't do it real accurately. I didn't draw a great exponential function, but with a little bit of help, we can construct one. Okay, and this one, the x-axis would be about here, and the y-axis would be about here. And again, it's not totally accurate, but it has this general shape. Now, what we can do with these functions, and this is a preview, you're not going to have to master this immediately. I can sketch my x and y axis any way I want to. And then I can construct, let's say, this graph. Let's have a 4x4 rectangle. Square. It should have made it a little bit higher, but it's giving you the idea. Oh boy, that looks great there. Not a very good parabola, kind of choke. Okay, so there it is. Now this function has a formula. We're not going to talk about the formula just now. I mean, I'll tell you it's y equals x squared, but we're not going to use that. But what we are going to do is we're going to go ahead and transform this graph. And there are many ways we can transform a graph. What we're going to do is we're going to move it. Oh, let's say we're going to move it over to here and up, so that bottom edge is here. Here's the red dot. Now we just moved the graph over. Well, I'm going to say the coordinates of the red dot are 5 and 3. Okay, x equals 5, y equals 3. So we just shifted the graph over here to 0.53. Now we've got a new function. Okay. If this function is y equals f of x, and we have a formula for it. We do, of course, it'd be x squared. And let's just, okay, let's f of x not x squared. Okay. This function would have a different name. Well, I use f for the name of this function. I'll use g for the name of this function. Now there's an expression I could write using function notation, but I'm going to leave it out because I don't expect you to understand function notation well enough yet, although some of you probably do. Okay, y equals g of x. And in this case, if I move this thing over faithfully, this function is going to be x minus 5 squared plus 3. Move 5 units in the x direction, which we did. The red dot moved 5 units over this way, 3 units up. We replace x in this expression by x minus 5. And then if we want y to go, we want to go up 3 units in the y direction, then we're going to add 3 to our y value. So there's a fairly simple logic. Again, you don't have to totally understand this. It's giving you a picture of what we can do. Okay, so we can move these graphs around. We can also change the shape of the rectangle. We can stretch it out this way. We can stretch it up this way. We can scrunch it down this way. Okay, so we might have another graph that would go in a much wider and compressed rectangle. Okay, a red dot might still go here. Our parabola would still have the same basic shape, but it would have to go through these corners and through the red dot, so it would look like this. Something like this. See how this comes out. Not as bad as usual, okay? We have a graph that looks like this. Now, these graphs also can be continued. Now, when we start, we confine our attention to what happens in this 4x4 rectangle. But if we go beyond the 4x4 rectangle, once we know the rules of the function, it's pretty easy to see what happens. This function would then continue, and I'll continue it like so. And this one would continue. Say this one. Continue gradually curve one more sharply upward. Okay. They continue forever. And this, okay. So these are part of an infinite parabola. And same infinite parabola here, just shifting over. A scrunch down parabola here. And stretch out, scrunch this way, stretch this way. So that we can get any parabola in the entire XY plane. Now that's a big deal because parabolas in the XY plane model a whole lot of really important stuff. And we'll see a little bit more about how that works. Okay, now we do the same thing with this graph or with this graph. We can also, I'll just do one more thing. We also, let's do one in narrow rectangle up here. We're going to put the dot at the top. Get this, we would have to flip this one over. Just to flip this one over, keep it on the x-axis, keep the dot on the x-axis, flip it this way, the dot still in the middle of its edge, but now it's the top edge. So the dot could go at the top edge. Again, don't worry about the details about this. Oh, it's a bad parabola. It's going to be a lot flatter in the middle. So I didn't draw a very good parabola there. Yeah, okay. So we get upside down parabola. Put an upside down parabola up here, put a wide one, narrow one, fat one, skinny one. Okay. They can go any place. So if you have a graph that means something, has a meaning, and if you know that the meaning is modeled by a parabola, well, you can do some interpretation and all kinds of stuff. But we'll leave it at this. We got these things. We can stretch them, compress them. We don't rotate them in this course. Okay, you have to have trigonometry to rotate these, and even then, it's kind of difficult, kind of challenging. Something you'll see a little of in second semester in calculus, but we don't touch it in this semester because we're not doing trigonometry. Okay, so there we have a little bit of a picture. Now let's just look at one more thing, what some of these things can model and why we're even doing this.